Hi everyone! In this video we're going to go over the last type of reaction, reduction-oxidation reactions. So in this reaction in particular that I'm about to show you, they're going to place zinc in a test tube of diluted hydrochloric acid. So the hydrochloric acid has some water in it just to keep it safe so it's not pure hydrochloric acid. But you might already notice that some bubbles are forming. So what's happening here is the zinc is actually dissolving in the acid solution. And it's going to slowly disappear over time. Now those bubbles that are forming are actually hydrogen gas, which is a flammable gas. So if you have enough hydrogen gas, you can actually cause an explosion, so you do have to be careful. Here, they're just generating a small amount, though. Now, once this reaction's complete, they're going to do a test to test for hydrogen gas, and that involves putting a lit match, into the test tube with the gas. So here they're about to do it. And it actually will make a popping sound, and then the flame will go out. So we'll do something similar in lab with magnesium and hydrochloric acid. And it's really cool to see those reactions and to hear that popping sound. All right, so again, the video we just watched showed zinc reacting with hydrochloric acid, and the zinc has to react with 2 molecules of hydrochloric acid in order for this reaction to work and to be balanced. In the products, we end up with zinc ions and chloride ions, and those are going to be dissolved in the solution. So we actually use this AQ symbol in parentheses, which stands for aqueous. So it's dissolved in water. So those ions aren't actually attached to each other just yet. Now, if we evaporated all the water out of the test tube, then we would see the crystals at the bottom, the ionic compounds. But when there's solution in the test tube, water in particular, the zinc ions and the chloride ions are dissolved. So this is really similar to when you add regular salt to water and it dissolves. If you evaporate that water off, you'll see the salt at the bottom. Same idea here. And then the other product is hydrogen gas, which we saw in the video. Those were the bubbles that were forming. Okay, so let's talk about what makes a reduction-oxidation reaction work. So in reduction-oxidation reactions, we're seeing an exchange of electrons. So we just saw our reaction on the previous slide. And because HCl and zinc chloride are aqueous, we can separate those into their dissolved ions. Now, zinc initially is just a pure solid, so we'll just leave that as is. And then HCl is going to break apart in solution. So this is what acids typically do. Acids like to give up hydrogen ions. So we'll end up with 2H plus and 2Cl minus, or chloride ions. And then in the products, we have zinc with a 2 plus charge, so it's become an ion. And then we still have our 2 chloride ions. And then finally, we have our hydrogen gas molecule. So looking at zinc chloride in particular, I knew this was an ionic compound because we had a metal and a nonmetal. So zinc is the metal, chlorine is the nonmetal. And I know in an ionic compound, chlorine always has a -1 charge, And because there are two of those negative charges, that means zinc must be a 2+ ion. Now, if we compare each atom in the reactants and the products, we'll start to notice that zinc went from being a neutral solid to an ion with a +2 charge. So that must mean that zinc lost electrons. So zinc loses electrons. But where are those electrons going? Because they must be going somewhere, right? Well, if we look at hydrogen, hydrogen starts out as a +1 ion, since it dissolved in solution. And in the end, it has 0 charge because it's now a diatomic molecule, which is neutral. So the hydrogen atoms gain the electrons. Now chlorine just stays the same. So notice that chlorine, we have a -1 charge in the reactants and in the products. So nothing happened to chlorine. Chlorine kept its extra electron to keep its -1 charge. However, zinc gave up its electrons to hydrogen. So this is very characteristic of a reduction-oxidation reaction. We have a transfer of electrons. All right, so let's simplify this a little bit. So if something loses electrons in a reaction, that process is called oxidation. And if something gains electrons, that process is called reduction. And because electrons have to go somewhere, oxidation always goes hand in hand with reduction. So down below, we have just a generic equation. Molecule A is reacting with molecule B. And initially, both molecules are neutral, so they have 0 charge. But in the products, notice that molecule A now has a +1 charge, and molecule B has a -1 charge. So that means that A, to become positive, had to lose electrons. And again, we said that the loss of electrons is oxidation. And then B, to have a negative charge, had to gain electrons. So that is called reduction. All right, so again, we've got loss of electrons is oxidation, gain of electrons is reduction. Now, there are a couple of acronyms that can help you remember which is which, because I still get them confused. So I use these acronyms as well. The first one is oil rig. So oxidation is loss of electrons. Reduction is gain of electrons. The other one is Leo the lion says grr. So loss of electrons is oxidation. Gain of electrons is reduction. So whichever acronym helps you the most, whichever one you like better, use that for oxidation-reduction reactions because it will help a lot. All right, so again, the atom that loses electrons is oxidized, and the atom that gains electrons is reduced. So in our example from earlier, A was the molecule that lost electrons, so it is oxidized, and B gained electrons, so it is reduced. Now, we can also think of this in terms of the effect that A has on B. So because A is giving its electrons to B, we can call that the reducing agent because it's reducing the other atom. And vice versa. So B is taking electrons away from A, so it's oxidizing A, which means that B is the oxidizing agent. Now, if that is confusing, the way that I remember this, I figure out which molecule or atom is oxidized and which one is reduced, and then they're going to be the opposite type of agent. So the oxidized atom is the reducing agent. The reduced atom is the oxidizing agent. So you always flip it. Whichever assignment they have, you flip it for the agent, if that makes sense. All right, so let's go over some rules for oxidation reduction. In order to figure out how electrons are transferred between atoms, we want to assign what are called oxidation states. And there's a few things that we do have to memorize a little bit, but it's not too bad. So the first rule is a neutral element has an oxidation state of 0. You can also sort of think of oxidation states as charges. So, for example, pure sodium has a charge of 0. It's neutral, doesn't have too many electrons, too many protons. It has the exact same amount of electrons and protons. So its charge is 0, which means its oxidation state is 0. And then chlorine, the diatomic molecule, also has an oxidation state of 0 because it is neutral. Now, the next rule says that an ion's oxidation state is the same as its charge. So, sodium as an ion always has a charge of +1, and that's also its oxidation state. And then chloride always has a charge of -1, so that will be its oxidation state as well. And that'll be true for any ion. Whatever its charge is, that's the oxidation state. The next rule says that hydrogen, when it's in a molecule like HCl, has an oxidation state of +1. And that makes sense. We said earlier hydrogen is in group 1 because it has one valence electron. And if it loses that one valence electron, it becomes a +1 ion. And then the next rule states that oxygen, when it's in a molecule like H2O, has an oxidation state of -2. And we know that from oxygen's charge as an ion. When oxygen is an ion, it has a charge of -2. But the reason that we're really stating this in particular here is due to the fact that oxidation states can apply to atoms in molecules. So, for example, in HCl and H2O, those are not ionic compounds. They're molecules, right? So they're sharing electrons. So the oxidation state isn't really a charge like in an ionic compound. It's a little different, but it is similar to an ionic charge. Now, the last rule says that halogens, so this would be fluorine, chlorine, bromine, iodine, they have an oxidation state of -1 when they're in a molecule. All right, so hopefully that isn't too confusing, but we're going to get some practice in. So let's look at a very simple oxidation reduction reaction. So in the reaction below, we're going to determine which atom is oxidized and which atom is reduced. Now remember from our acronym, oil rig, or Leo the Lion says grr, oxidation means loss of electrons. Reduction means gain of electrons. So we want to figure out what is losing electrons, what is gaining electrons. All right, so let's break this down. We have pure sodium to start. and that's reacting with a diatomic molecule, chlorine, and we're forming NaCl. So this is table salt, and we know that this is an ionic compound because we have a metal and a nonmetal. All right, so let's assign oxidation states for each one. So the oxidation state for sodium initially it is neutral, right? It's just pure sodium, it doesn't have a charge, so its oxidation state is 0. And then similarly, chlorine, Cl2, that's a neutral molecule, so that will also have an oxidation state of 0. Now, in the product, we have an ionic compound. So there was an exchange of electrons. And what is the charge on sodium when it is an ion? So remember, sodium is in group 1. It has 1 valence electron. So if it loses that valence electron, it will now have a positive 1 charge. And what about the chloride ion? What is the charge on that? So remember, chlorine is in group 7 of the representative elements. It has 7 valence electrons, and it wants to gain 1 more electron to have an octet. So if it gains 1 electron, it'll have an extra negative charge. So it will be -1. All right, so now we're going to compare. So let's compare sodium in the reactants to sodium in the products. So we went from 0 to +1. So does that mean that sodium gained electrons or lost electrons? It lost electrons. So we just said that sodium's in group 1. It has 1 valence electron, and it can lose that 1 valence electron. So it lost electrons. And according to our acronym up above, if you lose electrons, that is oxidation. And then what about chlorine? So chlorine went from 0 to -1. So did it lose electrons or gain electrons? It gained electrons. And remember, oxidation and reduction go hand in hand. So if you can figure out which atom is oxidized, that means the other atom is automatically reduced. So chlorine gained electrons, so it is reduced. All right, so let's just summarize that down below. So sodium lost electrons and was oxidized. And then chlorine, Cl2, gained electrons and was reduced. All right. So let's do another practice problem. And I'd like you to try this one on your own first. So in this reaction, we have iron reacting with oxygen to form iron oxide. So I would like you to balance the equation. That's what the blank spots are in front of each element or atom or ionic compound. And then determine the oxidation state of each atom in the reactants, and then do the same for the products. And then try to determine which atom is oxidized and which atom is reduced. So I'll let you try this on your own first, so feel free to pause the video and then we'll go over it together. All right, so let's balance this equation. So it looks like initially we need 2 iron atoms on each side. So we have 2 on the right, but only 1 on the left. So I'm going to put 2 in front of Fe. All right, and then we need to balance oxygen. So we have 2 on the left and 3 on the right. Ugh, how can we balance that? Well, one way to do it is just to multiply the oxygens on the left by the subscript on the right. So we'll multiply O2 by 3, and then we'll do the same thing for O3. We'll multiply that by 2. And that should give us a total of 6 oxygens on each side. So on the left we have 3 times 2, so that's a total of 6. And on the right, we also have 2 times 3, which is 6. Perfect. However, when we put that 2 in front of the product, we actually increased the amount of iron. So now we have 2 times 2, 4 iron atoms on the right. So I'm just going to go back and adjust my original number of iron atoms to 4. That way everything should be balanced. So the ratio is 4 to 3 to 2. So when you're balancing reactions, remember you can always go back and forth and adjust things as needed. I usually have to do that as well. Okay, so now that we have the balanced equation, those coefficients actually don't matter when we're assigning oxidation states. So ignore the coefficients when you're assigning oxidation states. So for example, let's say something had a +1 oxidation state, but a coefficient of 2. We don't want to multiply the oxidation state by 2. It's just going to be +1. So up above, let's assign the oxidation states for the reactants. So iron is just neutral. It's just an atom. So that has an oxidation state of 0. And I'll just label this oxidation state here. And then what about O2? So that's a diatomic molecule. It's not an ion. So that is also neutral and has an oxidation state of 0. And now let's look at the product. This is an ionic compound. We have a metal, iron, and a nonmetal oxygen. Now, iron is one of those atoms that can have multiple charges depending on what it's bonded to. So let's see if we can figure out what its charge is. So we'll base it off of oxygen. So we have 2 irons and 3 oxygens. And what is the charge on an oxide ion? -2. So remember, oxygen is in group 6 of the periodic table, if we're just looking at representative elements. So it needs to gain 2 electrons to have an octet of electrons, like a noble gas. So that means if it gains 2 electrons, it will have an overall -2 charge. So that's true for each oxygen. So that will give us a total of -6 from the oxide ions. And remember, in ionic compounds, we want our charges to cancel each other. So our 2 iron ions have to total +6. So if we divide up that +6 between two irons, what do we get? +3 for each iron ion. And remember, in our list of rules, it said that the oxidation state is going to be the same as the charge on the ion. So that means that iron has a +3 charge in the product and a +3 oxidation state, and oxygen has a -2 oxidation state. But like I said earlier, we're going to ignore the coefficients. So we're not multiplying +3 by 2 or -2 by 2. We're just assigning an oxidation state. We're ignoring the coefficients. Okay, now the last question, which atom is oxidized and which atom is reduced? So let's compare iron in the reactant and in the product. So iron went from 0 to +3. So did it gain electrons or lose electrons? Well, to become positively charged, it had to lose electrons. Now, is loss of electrons oxidation or reduction? Oxidation, oil rig, right? All right, so then let's compare oxygen in the reactants to the products. So oxygen went from an oxidation state of 0 to -2. So did oxygen lose electrons or gain electrons? It gained electrons. And that means it was reduced. All right, so for question 4, we can write that iron is oxidized and oxygen is reduced. Okay. So hopefully it's not too confusing. I know it always takes a bit of practice with redox reactions before it really makes sense, but it is an important concept to understand because if you go on to take a biochemistry related course, redox reactions are everywhere in biochemistry. For example, in cellular respiration, the oxygen that we inhale from the air around us is oxidizing sugars into carbon dioxide and water. And this is what provides energy to living cells. So down below, I have that reaction listed. So glucose, which is a sugar, will react with oxygen and produce carbon dioxide and water. And again, this is a redox reaction. So electrons are exchanged and energy is released during this process. Now, the opposite is also true. So plants actually carry out redox reactions that makes life possible. And this is through a process called photosynthesis. So this is going to be the opposite of cellular respiration, where plants can combine CO2 from the air and water and then produce glucose and oxygen. Now, of course, this is going to require energy, and plants will get that energy from the sun. So we could even write that energy is going into that reaction. So again, redox is really important in not only chemistry, but all around us. In our bodies, it's constantly occurring. There's always an exchange of electrons happening. All right, so that is the end of chapter 5. And in the next video, we will start chapter 6. I will see you then.